Okay, so let's do some examples of working with equally likely, the assumption of equally likely outcomes. So, first of all, let's suppose we roll a die and we see what comes up. So what are the possibilities here? A die is a six-sided, it's a cube, has the numbers 1 through 6 written on each side, so the possibilities are 1, 2, 3, 4, 5, and 6. That is my sample space. So the number of things in my sample space is 6. What is the probability of any of these numbers coming up then? It seems reasonable that so long as the die is fair, that is that nobody's trying to cheat you by giving you a die that comes up more on one side than the other, that the probability should be 1 over ns, which is 1 over 6. 1 out of 6 times you should expect to get a 1, or a 2, or 3, or 4, or 5, or 6. So this makes sense for us to assume that things are equally likely. Now here's a fact. If E is a compound event, an event that has more than one outcome in it, then under the assumption of equally likely outcomes, the probability of the event is just the number of things in that event divided by the total number of things in the total set. So again, just a simple example is, what's the probability of getting an even number after, when rolling a single die? This is the probability of getting a 2, 4, or a 6. And so how many things are in 2, 4, 6 versus the total sample space? That's 3 divided by 6, that's 0.5. So half the time I should expect to get an even number. Again, that seems pretty intuitive. Now let's do some examples that use counting. So here is a first example. Let's look at rolling 2 dice again. Now, I keep saying that the sample space is all pairs of numbers x and y such that x and y are between 1 and 6. But let's make this really explicit. Let's say one die is blue and the other is red. Let x be the number that comes up on the blue die and y the number on the red die. So then we can look at rolls of the dice as pairs x, y, where x and y are between 1. Okay. And here maybe it makes more sense why then. So 1, 2 is different from 2, 1, since 1, 2 means the blue is 1, the red is 2, while 2, 1 means the blue is 2, the red is 1. Okay. Now, what is the sample space? It's going to be all pairs x, y, where x and y lie between 1 and 6. Now, how big is S? Well, we use the multiplication principle here. How many, we're going to use the multiplication principle. So how many, what is the first operation? The number on the blue die. What is the second operation? It's the number on the red die. How many choices do I have for the number on the blue die? 6. How many for the number on the red die? It doesn't matter what the blue die is. It's also 6. So the total number of ways of rolling the 2 die is 6 times 6, which is 36. Makes sense. 6 choices for x, 6 choices for y, so 36 total ways. Okay. Now, this means that, for example, what is the probability of any specific roll? This will always be 1 over the number of things in S, which is 1 over 36. So this means like the probability of getting snake eyes 2 ones is 1 over 36. The probability of getting a 3 and a 4 is also 1 over 36. The probability of getting a 4 and a 3 is also 1 over 36, etc. B, let's look at something a little bit more difficult. How about the probability that the total is 2? Well, I look at the total number of ways that I could get a 2. Well, since the numbers are between 1 and 6, the only way that I could have two numbers that add up to 2 is to get a 1 and a 1. So this is just how many things are in set 1 and 1 over ns? Just 1. So the probability of getting a total of 2 is 1 out of 36. How about the probability that the total is 7? Well, there are a lot of ways of rolling a 7. I could get a 1 and a 6. I could get a 2 and a 5. I could get a 3 and a 4. I could get a 4 and a 3. I could get a 5 and a 2. Or I could get a 6 and a 1. Now the probability here will be the number of things in the ways that I can get a 7 divided by the number of things in the set. Now the number of ways I can get a 7 there are 1, 2, 3, 4, 5, 6 ways. So 6 divided by 36 is 1 over 6. So 1/6 of the time I expect to get a 7. In fact, it is the most common roll in terms of the probability that whatever of them come up. How about what is the probability that I get doubles? Well, how many ways can I get doubles? I can get a 1 and a 1, I can get a 2 and a 2, I can get a 3 and a 3, I can get a 4 and a 4, I could get a 5 and a 5, or I could get a 6 and a 6. Well, that's not a surprise. If I'm saying I'm getting doubles, the number of ways to get doubles is x can be anything, but then y has to be x. I could have counted this using the multiplication principle. So my first operation is, the roll of the blue die. My second operation would be the roll of the red die, but it has to equal the roll of the blue die. So the number of ways of getting the blue die is 6. The number of ways of getting the red die is 1, because once I've chosen what the blue die is, the red die has to equal it. So the total number of ways of getting doubles is 6 times 1 is equal to 6. Anyway, so the probability of getting doubles, again, is the number of ways of getting doubles divided by the total number of rolls, which is going to be 6 divided by 36, which is 1 out of 6 times. You expect doubles 1 out of 6 times, so if you're playing like Monopoly, great. 1 out of 6 times that you roll the die, you should expect to get doubles. Great. Let's look at something a little bit more difficult. Let's say I have 10 batteries in a box, and 4 of them are charged, and the 6 of them are not. And so I need 2 for my remote control, and I choose 3. Okay, I choose 3 at random. I can't just look at them and say which ones are charged and which ones are not. So before we get down to counting probability, let's think of what the sample space here should be. And again, we're going to want to use equally likely outcomes here. So what are all the different outcomes? My outcomes should really be each way I can choose 3 batteries from the 10 in the box. Okay, any possible way of choosing that. Now let's notice that we are choosing without repetition, because once I pull a battery out, I'm not going to put it in and take it back out twice, because I want to find 2 batteries. If I keep pulling the same guy out, even if it's good, I can't stick it into my remote control twice and hope to work. Anyways, choosing without repetition, but the order that I choose it in doesn't matter, because the set of 3 batteries is just the set of 3 batteries. I just pull out 3 batteries. Even if I and to check which ones of them are good. Whether they're good or not doesn't really affect the order that I pull them out. So this means that this is a combination. So how many ways can, so if S is equal to the ways of choosing 3 batteries from 10, then the number of ways of doing this is 10C3, because I am choosing 3 batteries out of the 10. And just using my computer, this is equal to 120. Let's remember what the formula is. It's 10 factorial divided by 3 factorial times 10 minus 3 factorial. You can compute that, but for the sake of time, that's 120. Now let's ask some and this makes sense that any of these should be, why does equally likely, why is this equally likely? Because I'm choosing at random. So when I'm choosing at random, that really means equally likely. So when I say choosing at random, this means equally likely to choose any 3 instead of batteries. Okay. So let's ask some specific questions. What is the probability that I choose at least 2 good batteries? Actually, let's ask a simpler one. The probability that I choose no good batteries. Well, this is going to be the number of ways that I can choose no good batteries divided by the total number of ways that I can choose any 3 batteries. Now, the number of ways that I can choose no good batteries, that's the number of ways that I can choose 3 bad batteries. So I'm choosing 3 bad batteries out of the 10 minus 4 equals 6 bad batteries. There are 4 good ones, there are 10 total, so 6 of them are bad. So the number of 3 bad is equal to 6 choose 3. Now what is 6 choose 3? This one shouldn't be too hard for you to actually sit down and compute yourself, but this is going to be 6 factorial divided by 3 factorial divided by 6 minus 3 factorial, and it's equal to 20. So the probability of no good batteries is the number of ways of having 3 bad batteries divided by the total number of ways of choosing 3 batteries, which is 20 divided by 120, which is equal to 1 out of 6. That number keeps coming up, sorry, but 1/6 of the time I will pull up no good batteries. How about a second question? What is the probability that I get at least 2 good batteries? I want 2 good batteries, so if I pull out at least 2 good batteries, I'm happy. If I pull out 3 good batteries, great, I only need 2. Well, this is going to be the probability that I have at least, this is going to be the number of ways that I can pull out at least 2 good batteries divided by the number of ways I can pull out 3 batteries. Now, the number of ways that I can pull out at least 2 good, well, there are 2 ways I can pull out at least 2 good batteries. I can pull out 2 good and 1 bad, or I can pull out 3 good batteries. Okay. So what does that mean? These are disjoint possibilities. If I pull out 2 good batteries and 1 bad, then I can't also have pulled out 3 batteries. So that means that to count the number of ways of having at least 2 good, I add up the number of ways of having exactly 2 good and the number of ways of pulling out 3 good batteries. So I need to add these up independently. Okay, so what's the number of ways of having 2 good batteries? This means that I have, if I choose 2 good batteries, I also choose 1 bad battery. So I have 2 operations. This is going to be the multiplication rule. My first operation is choosing 2 good out of the 4. My second operation is choosing 1 bad out of 6. The number of ways of doing the first one is 4 choose 2. There are 4 total good batteries, and I'm choosing 2 of them. And the number of ways of doing that should be 6. So this is 6. The number of ways of choosing 1 bad out of 6, well, you could write it as 6 choose 1, but this number is also 6 because, hey, I'm just choosing 1 out of 6. There are 6 ways to do that. So the total number of ways of choosing 2 good is 6 times 6, which is 36. How about the number of ways of choosing 3 good? Well, this is going to be, there's only one operation here. I'm just choosing 3 good out of the 4. So this is 4 choose 3. Check it. The ways of doing this is 4. So the ways of choosing at least 2 good is 4 plus 36, which is 40. So that means the probability of at least 2 good is equal to the number of at least 2 good divided by the total number of ways of choosing 3 batteries, which is 40 divided by 120, which is 1/3. So a third of the time, if I only pull out 4 batteries, I'm going to end up with 2 good ones. So I should probably pull out a little bit more than just 4 batteries. Okay, let's look at another example. 3 cards. Let's suppose that I'm playing Texas Hold'em, which means that I get 2 cards face down. Now, what are good hands? It's good for me to have 2 cards of the same suit or 2 cards of the same rank. So either suited cards or a pair. But first, my question, what is my sample space? It's going to be all possible combinations of 2 cards from 52. The order that I get the cards in doesn't matter because that doesn't actually affect the hand I have. If I could pick up the 2 cards and flip them around, it doesn't change the hand I have. So the number, the number of things in my sample space is 52 choose 2, which is actually a fairly small number. 52 choose 2 is, well, okay, it's not tiny, but it's 1, 3, 2, 6. Now let's look for some possibility. What is the probability that my cards are suited? So suited means cards are the same suit. Remember, this is hearts, diamonds, spades, and clubs. Okay, so what is the probability that my cards are suited? Well, this is the number of ways that my cards could be suited divided by the total number of ways I can get my cards. Now, what are the total number of ways that my cards could be suited? Let's think about this. There are really 2 operations. The first operation is let's choose a suit, so all the possibilities for the different suits. The second operation here is how many ways can I get 2 cards of that given suit. Now the number of ways that I can get 2 cards out of a given suit is independent of which suit I choose because there are always 13 cards of a given suit. So the number of ways I can choose a suit is 4. The number of ways that I can get 2 cards out of that given suit is 13 choose 2 because there are 13 cards of a given suit. And I'm choosing 2 of them to be in my hand. So that's 13 choose 2, which is 78. So the total number of ways of having a suited hand is 4 times 78, which is 312. So the probability of getting suited is the number of ways of getting suited, which is 312, divided by the number of ways of just getting hands, which is 1326, and that simplifies to 4 over 17, which is equal to about, give me a second, 0.23529, ... So just under a quarter of the time, I can actually expect to get 2 cards of the same suit. Interesting. Okay. Kind of makes sense, though. Maybe. How about B? What is the probability that I get a pair? Well, again, let's look at this. This is the number of ways of getting a pair divided by the number of ways of getting, a hand. Well, when choosing a pair, there are, again, two operations. I choose a rank, and then I see how many ways of getting, and then, getting a pair of that rank. My first operation is I choose a rank, and my second operation is I choose 2 of the 4 cards of that rank. So the number of ways of choosing a rank, there are 13 ranks. The number of ways of choosing 2 cards of the 4 of that rank is 4 choose 2, which is again 6. So the total number of ways of getting a pair is 13 times 6, which is 78. Where did 78 come up before? Oh, right, 13 choose 2. Yeah, 13 times 6, 78. Okay, so that means that the probability of getting a pair is the number of ways of getting a pair, which is 78, divided by the number of total different possibilities, which is 1326. So this is equal to 1 out of 17, which is approximately equal to 0.0588 blah 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 percent of that much of the time. So about 6% of the time. So I'm usually not going to expect to get a pair. Okay. Finally, let's look at how I can look at, say, what example was this? Was this example 3, 4? Percentages as probabilities. Now, what exactly do I mean by this? Well, I can think of percentages as probabilities as such. Say 40% of people approve of Obama's job performance. I don't know what the actual number is. I can interpret this as saying that the probability I choose an American at random and that they like Obama's performance is 0.4, because that's what corresponds to 40%. So, okay, I interpret the percentage of people as saying I'm choosing an American at random and asking whether they like Obama. And so I'm suddenly changing a percentage into a sort of an experiment. It's like I'm polling. And the flip side to that is if you're polling, then you can get in information about percentages. So you poll to collect some data, and that gives you some percentages. So as an example, New York City has about 8 million people in it, and Brooklyn has about, let's say, 2.5 million people. So the percent of people who live in Brooklyn is 2.5 million divided by 8 million, which is equal to 31.25%. So just under a third of people, of New Yorkers, live in Brooklyn. But I can think of this again as a probability. The probability that you live in Brooklyn is the number of people who live in Brooklyn divided by the number of people who live in New York City as a total, which again is this number 2.5 million divided by 8 million, which is 0.3125. So probabilities, I can use the theory of probabilities to talk about percentages. I'm not even necessarily talking about random events. I can just be talking about the percentages of populations as a whole. I can treat them as random events if I imagine that I'm picking a person from that population at random, which means that I'm equally likely to choose anybody from that population. But then I can use the tools of probability to help me work with percentages, and we'll see that later. Oh, I'm stuffed up.